Automated machine learning is well known for making machine learning much easier to use for non-experts. But what do you do if you have no labels? For example, take unsupervised anomaly detection, where your goal is to identify the unusual data points, which could correspond to security threats or diseases. Anomaly detection algorithms map each data point to an anomaly score. The higher the score, the more anomalous the data point. If you know the percentage of anomalies in your dataset, that is, the contamination factor, you can convert your anomaly scores into predicted labels. However, in our experience, most users don't actually know if they have a large number of anomalies or a small number. And so in practice, the contamination factor is unknown. Nevertheless, there are a large number of different machine learning-based anomaly detection methods out there. But this, of course, is itself its own problem. How do you know which one of them you should use for your given dataset? In this case, we're given a particular dataset and a set of models, or even a set of hyperparameter configurations for a single model. And our goal now is to choose the best one. To the best of our knowledge, there's only a single method out there for solving this problem, and it's called MetaOD. MetaOD requires a set of historical datasets with labels. It then learns an embedded dataset representation so that it can compare your current dataset with all of the historical ones to find the ones that are the most similar. Using this, it can predict the model that it believes is going to be the best for your dataset. We propose an alternative framework, N-1 experts. The key idea is to leverage the complementary strengths between each model. To do this, for each candidate model, we first obtain a set of predicted labels. We use the predictions from the other models as expert labels to evaluate the quality of each candidate model. In particular, we look at the agreement between the labels. Now you may be wondering, how do we calculate these labels given that we don't know the contamination factor? Of course, if you do know, you can just plug it in and use it, no problem. What we found works pretty well in practice is to simply repeat this process and average over multiple contamination factors. We performed some experiments to evaluate N-1 experts with MetaOD. In particular, we looked at 14 diverse open source datasets, ODDS, as well as 8 software security log-based datasets from an industry partner. We looked at 8 different models, each of which had optimized hyperparameter configurations, designed to perform well on average across a broad range of different anomaly detection benchmarks. We measured the quality of each model in AROC, and we evaluated our model selection techniques using the regret. That is, the distance in the AROC from the best model. We hypothesized that MetaOD would do the best on the software security log datasets because they each come from a similar application. In practice, we actually found that on most of our datasets, N-1 experts outperformed MetaOD. And you can see this because almost all of the datasets here are above this black line, which means that N-1 experts has smaller regret. All of the points that are drawn in red are statistically significant across our 15 independent trials of each method. We also saw it's possible that N-1 experts has a bit of an advantage here, because all of the models that we're working with have strong hyperparameter values, which means they correspond to experts. So we repeated this experiment again, but this time with 5 random hyperparameter configurations for each of our 8 models. In this case, we still saw similar results. N-1 experts continue to perform the best across the largest number of datasets, even when not expected. So we introduced N-1 experts, the first fully unsupervised UAD model selection algorithm. It outperformed the baselines we evaluated against, even on the correlated software security log datasets and the randomly configured models. It would be interesting to still evaluate N-1 experts, but this time in the context of hyperparameter optimization or combined algorithm selection and hyperparameter optimization. It would also be interesting to compare it against ensembling techniques, which are intuitively related. Finally, it may be possible to add some enhancements to counteract the situation that can arise if you have a large number of poor quality expert models. All of this research was done at Oracle Labs on the Automated Machine Learning with Explainability team. We have a large number of research teams here at Oracle Labs, and we'd be very happy to hear from you. You can either reach out or go online to learn more.